as well as sharing some of the insights of my simulation model, which I've designed, as well as some of the outcomes and results. So, autonomous robots are an innovative technology deployed in last mile delivery to alleviate some of the existing pressure in this last step of transportation towards final customers. The first very important thing to mention is that they're living in the pedestrian world, meaning that they're using zebra crossings and pavements to move around the urban environment. If this, on the one hand, allows them to avoid some of the traditional problems related to truck delivery, on the other, it highly affects some of their characteristics. You can see from the image, the size of the vehicle is quite small, and consequently, the size of the payload, the amount of payload which can be carried around is also limited, forcing the robot to serve only one customer for every mission. Also, when we look at the speeds that these vehicles travel at, we have limited speed for safety reasons, with a maximum speed of 6 kilometers per hour. Battery duration, on the other hand, doesn't allow them to work for more than 2 hours. After that, robots are forced to get back to a depot recharging. So if we combine these different factors, we understand that the perfect scenario of application is a local delivery, where these orders delivered are small in terms of size. My work has started considering what has been done in scientific literature concerning the field of automation and last mile delivery, and the relevance of the combination of these two is connected to a wide number and variety of different topics, which I found as active streams of research. If we give a look at what has been done, we see that, for example, the main vehicles which have been considered are autonomous drones and autonomous vehicles, and this little alternative, autonomous robots, hasn't been the focus of the studies. Also, when we look at the industry, food delivery has received little attention compared to the general e-commerce industry, despite the relevance that last mile delivery plays in food delivery. So, with the objective of filling the existing gaps in scientific literature, the objective has been to understand what are the most important parameters for the deployment of delivery robots in food delivery, as well as understanding what are the conditions of economic profitability. So, aside from an additional review on food delivery, as well as on automatic guided vehicles, a discussion with a manager of Deliveroo has been conducted to get some useful insights about the industry. And a wide variety of different parameters have been identified as important to include in the modeling, and to deal with this type of complexity as well as with the complexity of the system to design, I decided to use a simulation model using agent-based modeling as the modeling methodology. The software which has been used was AnyLogic, one of the only professional softwares available for agent-based modeling. Agent-based modeling allows the designer to concentrate on the constituted elements of a system and main actors called agents through the definition of their behavior as well as the interaction among one another. We see that in my case, I considered orders, customers, restaurants, robots, and platform as the main agents to design. So the analysis consists in a sensitivity analysis conducted on each of these parameters singularly, considering a starting base case, which is involving a central depot serving a squared area. Additionally, 2 different order profiles have been considered for each of the sensitivity analysis conducted. The first one aims at recreating the stress caused by lunch and dinner time on the order profile, and the second one, on the other hand, is a uniform distribution, used to see what are the effects of the peak of demand on the system. So I want to guide you through what happens in food delivery as well as in my model. Everything starts with the customer issuing the order. This triggers the preparation and the creation of the order agent in the restaurant which has been selected by the customer freely inside the area. And on taking the preparation time, we can find a very, very important variable, which is the earliest pickup time for the robot. As soon as the customer issues the order allocation activity has to take care of assigning this customer to only one of the robots of the fleet. As soon as possible for the robot moves towards the restaurant location, allowing to identify potentially the pickup time. Here, the robot needs to be loaded, and then can finally proceed towards the final customer, completing the delivery. After reaching the customer's location, it needs to be unloaded, and then the customer can finally retrieve what has been ordered. The time elapsed between the order issuing and the customer retrieving the order is the order cycle time, which is a very, very crucial and important factor in this industry, since most of the orders are not planned in advance. customers are willing to have their orders delivered as soon as possible. And obviously, order cycle time minimization is at the center of the optimization. But instead of considering the entire order cycle time, my analysis has focused on a concept, which is lateness. We can define lateness as a delay of arrival of a robot with respect to the earliest pickup time. You see here in the image, it's highlighted with a red line. In this case, the lateness can be calculated as the difference between the actual pickup time and the earliest pickup time, but for how the system has been designed, it is possible for robots to arrive before the earliest pickup time. In that case, obviously the robot cannot go back to the order, and the lateness value is equal to 0. So here you see in the lower part of the slides all the different components of the order cycle time, and you see how some of these have been considered deterministic, such as the order preparation and loading and unloading activities, while some others are a function of the status of the system as well as the parameters that I have analyzed. So I designed 2 different heuristic algorithms to take care of the order allocation process. I'll be discussing the one that I've used for most of the experiments. The name is look ahead immediate permanent assignment. And it's a heuristic algorithm which aims at identifying the robot in the best condition to serve the customer as soon as possible, assigning the order immediately and permanently to that unit. So the objective function considered is a weighted sum of lateness and energy consumption. And the 2 weighting factors are made so that lateness is prioritized with respect to energy consumption. And essentially, the second part only plays an active role in case 2 or more robots have a lateness value equal to 0. The factors which are influencing the value of lateness is very high. There's the position and time at which the robot can start the mission, as well as the condition of the battery. Because if the robot doesn't have enough battery, it's forced to get back to the depot, conducting a swapping activity, which is requiring 5 minutes. So here you see the environmental simulation, which has played a very, very important role in allowing me to understand if the code that I was writing was essentially modeling properly the system. Something that I want to point out is that from each of the runs, the position of restaurants and customer changes to avoid that any specific network configuration might negatively affect the generatability of the results. Speaking about results, I want to focus on what happens considering the base case with 2 different order profiles. Here you see the first one, the custom probability distribution in the 12 hours considered. The average order cycle time is highly affected, you see here from the image, is highly affected by the shape of demand. This is a clue of the fact that considering the number of robots that I've included in the start base case, the system is not capable of keeping up with requests, leading to an accumulation of orders, which ultimately leads to higher order cycle times during peak hours. If we compare it to the uniform distribution, we see on the other hand how, first of all, the average order cycle time is way lower, with values which are ranging around 33 minutes. But also, we cannot clearly see that there's an accumulation of orders in this very specific case. If we combine this information with the analysis conducted on the number of restaurants, we first of all clearly see how increasing the pickup density positively affects the system. But combining these 2 analyses, we can suggest companies that are willing to deploy this technology in the context of persistent delivery to try to have as many pickup points as possible, as well as increasing the variety, to try to act on the shape of demand, trying to be as close as possible to uniform distribution. If we give a look at, on the other hand, what happens in the case of the sensitivity analysis conducted on the size of the area and the speed, we do not discover anything new, but we clearly see that the larger the area, the worse are the results, and the higher the speed, the better are the results. But the size of the area and speed do not only influence lateness, but they actively act also on the travel time. And this raises the importance of these 2 parameters, letting me say that the choice of the environment of application for this type of technology is especially important because it's affecting one of the more than one of the components of the order cycle time. Currently, the applications are in university campuses, for example, where the network distance between points can be considered Euclidean, and the speeds which these vehicles can travel at is quite high. On the other hand, if we consider economic analysis, the scenario is completely different because it's true if we increase the size of the area, we're going to have worse results if we keep everything else the same. But from an economic perspective, increasing the area leads to a higher number of customers which can order through our application, potentially leading to higher revenues. So the experiment here is a little bit different. I've considered different sizes of areas, 5 different sizes of areas, combined with 4 different densities of customers. And to evaluate in which of the combination of these two, the scenario proves to be more profitable. So we can identify some scenarios of small areas, high densities, and so on and so forth. And the base of the experiment has been the calculation of the minimum number of robots required to maintain an average order cycle time of 35 minutes for extensive experiments. From this number, I've evaluated the investment cost, which is equal to €5,500 per each unit, as well as some other operational costs, which are included, and you see this here in the slides. Some of them are the outcome of the simulation, such as the energy. Some of them have been taken from what has been declared by the CEO of Starship Technology, the main company considered for this subject. In my opinion, it was very interesting to consider this type of scenario because, again, it's true if we increase the area, we're going to have high revenues, but at the same time, the number of robots required to maintain an average order cycle time of 35 minutes is going to increase more than linearly, leading to worse results in terms of investment and investment cost as well as in the operational costs. So it's not easy to understand what is the best combination. So having a look at the results, we clearly see how €2 per delivery and €4 per delivery do not allow the system to reach profitability in any of the scenarios considered. We can clearly see that how it starts to be profitable in the case of small areas and high densities, in the case of €4 per delivery, but all of the other combinations are negative. Well, if we increase the price to €6 per delivery, the story is completely different. The weight on revenues is playing a bigger role here, and so we see that almost all the combinations lead to profitable results. Something that I want to point out is that 60 customers per day per square kilometer do not lead to any profitable results for all the combinations considered with the price levels, which range from 2 to €6. So finally, obviously my work is presenting a lot of documentation concerning the building hypothesis of the model, related also to the novelty of the study as well as the current application of technology. An example might be the fact that in my system, the customer are free to order from any of the restaurants in the area. This hypothesis might not be true. Also, there's no specific network imbalance in my system. In reality, some restaurants might receive more requests than others. So I think that future research, on the other hand, should try to concentrate on specific case study, which in my opinion might be probably the best thing to do, and also try to evaluate what is the outcome of similar scenarios with alternative delivery methodologies, such as, for example, riders that we see currently going around. So that's it for my presentation. I thank you very much for your attention.
Congratulations for your work. It's been a pleasure to read your thesis. I have 2 questions about methodology, and so based on what I read. First of all, in the thesis you propose 2 different order of policies, and it's not clear to me how you chose these 2 policies and not others, and therefore the relationship between the choice of these 2 policies and the results of your literature review.
Okay, so the novelty of the study forced me to elaborate something new for the order allocation process. As I mentioned, I've conducted further research on automatic guided vehicles and order allocation. Some of the results I haven't put in the study, which belong to a previous literature review that I've conducted. Essentially, I tried to get some of the information coming from some of the studies which I've read, which I've seen that implemented some sort of combinatorial optimization. This is what I've done for the other method, which I have not presented. And also I've seen that some of the results, some of the studies that I've considered, on the other hand, one of them is listed in the literature review, is including this look ahead possibility to deal with the complexity from a computational perspective of the type of problem that I was dealing with, which is a scheduling problem, which obviously leads to a lot of different constraints. I tried to elaborate something new which could allow me to fit specifically the case in which I was considering. And so this is why I came out with new ways of assigning orders. Specifically, I've chosen this one, look ahead, limited permanent assignment, because it allowed me to look at larger experiments, while the other one, which is including a simple combinatorial optimization, was quite long in terms of computational time, allowing me to study systems only which could reach up to 7 robots, while in this scenario, obviously, to consider the areas of 1.25 square kilometers, the number of robots reaches 30 in the system. So,
second question, as you said during your presentation, it's clear that in every simulation you have to introduce some assumption. And for instance, in the thesis you say that as regards the type of distance, you assume to work with Euclidean distance and not rectilinear distance. Or else, you assume, as we saw, you assume a certain profile of demand with the 2 peaks, or a certain cost structure where, strange for me, the upfront cost of one robot equal to 5,000 euros. So the question is, how did you make all these assumptions based on what?
So let me get back to a slide, which I think is suits more your question. A lot of animation, sorry. So I think this is probably the best slide to present. Here you see all the different starting values which I've considered. Hopefully this answers your question. Some of these data starting value were collected with the discussion with delivery. For example, the density of restaurants per square kilometer, as well as the number of orders per day. So are a direct outcome of what is currently happening in the city of Milan. Some of the values, for example, referred to the specific robot are collected from the direct document, which is available online on the delivery robot version of Starship technology. As far as the order profile is concerned, so here I found an article on Chinese e-commerce about food delivery, which was presenting a similar distribution function, which wasn't quite like this. Was presenting a higher peak during the lunchtime and a different peak, completely different from a triangular distribution during lunchtime. So it was my intention to avoid being so specific with distribution order profile, which was not belonging to the country I belong to. I've been to China, so I know that there things are a little bit different. It's not just a matter of the time of the day, but it's a matter of sort of how people order. So I wanted to be the distribution function, the order profile as general as possible. So considering the triangular distribution for a single peak was, in my opinion, the best choice because it was, on the one hand, very easy to implement, and on the other was also very similar to what was happening in the study done by the other researchers. Including two triangular distribution, on the other hand, was done on purpose to avoid creating any sort of, again, of characterization of higher demand during dinner and during lunch, which I think might be the case of some areas, but also might be cases of other areas of application. I think that the real problem with this study is that being very general doesn't really allow you to understand if the technology is good, because I think the specific case studies, on the other hand, might be truly beneficial because everything is going to change depending on the number of restaurants that you have in the area and so on.
Bella zio.
Sì, intanto viene Caterina Rizzuri.
Là c'è papà.